Good morning everyone and welcome to this lecture on vector operations. Today we'll be talking about vector cross product, scalar triple product and triple cross product. So all these operations are operations involving vectors. In fact, we'll be putting the epsilon, that is the permutation symbol, and the Kronecker delta into practice by applying them for vector operations. So this lecture is going to stress upon the use of indicial notation for solving vector operations. So let's get started. So the first vector operation we'll be talking about is the vector cross product. So the cross product between two vectors, let's say u and v, typically till now we've been writing that as a determinant. So let's write it down. So u cross v is the determinant with the rows as e1, e2, e3, and then we have the components of u and v, that is u1, u2, u3, and v1, v2, v3. So this is how we used to evaluate cross products between two vectors till now. But now that we have been equipped with the indicial notation, so we learn how to write this in some sense like a closed form without writing this determinant using indicial notation. So let's write it down using indicial notation. So just as we did in the vector dot product, we will write u as ui ei. Remember, we don't need to put a summation sign because we are using the summation convention. And then we write cross with vj ej. Now since this is one complete mathematical term, so we cannot repeat the index I while writing the vector v in the indicial notation. So we have chosen the index j because if we had written vi ei along with ui ei, then I would have appeared more than 2 times, which is not allowed in our current choice of notation, that is in the Einstein notation. So we have to choose different indices, and again this is something that we learn with practice, because in very long expressions we may end up making a mistake by repeating an index, and we may realize after a few steps that we have done some sort of a blunder. So be careful in the first go when you write symbolic notation into indicial notation, that you do not repeat indices in for more than twice, right? So this case we write this as uiei cross vjej, and I'll make a note here that use different indices for u and v, right? So the next step is to move the scalar components u and v on the left hand side, because they do not participate in the cross products, they simply can be moved out of the cross product. So ui and vj are scalar components of the vectors. So now we are left with is ei crossed within ej, and e's are unit vectors, remember that. So in this case, when we are taking cross product of e, I and ej, if you go back to the last lecture's notes, you would see that in the previous lecture, when we talked about the permutation symbol and its identities, we had derived this expression where we had written ei cross ej using the permutation symbol epsilon. So we can write this as epsilon ijk ek. And this is a very important relation, in fact, because this allows us to write the cross products between unit vectors using epsilon. So this is the major motivation of bringing in the symbol epsilon, the permutation symbol, into our discussion in indicial notation and in this course. And it's typically done that we keep the epsilon on the left hand side. This is also a scalar. Remember, the values it can take is 1, -1 and 0 depending on the situation. So this also moves to the left hand side, and we have this expression, which is the expression for the cross products between u and v using the indicial notation. Now if you expand this, because remember the indices I, j and k, they are all repeated here. So this will expand. You will put 3 summation signs and expand this. In fact, we'll be dealing with some problems in the tutorial and assignment where I'll give you an expression to expand and see its value. So here if you expand it and you expanded the determinant form, you will get the same answer. And that should be the case because the final answer is the same. This is just a notation that we have chosen. But you can see this is quite compact and it's like a closed form because we don't have to write a determinant and then expand it. So it's all general in the indices I, j and k with the summation implied. So the whole idea here for me is to give you um, an understanding that indicial notation is very powerful, and that is the whole reason we are learning this notation. And this notation, as we'll see through lots of examples today and later in the course, will help us simplify things very effectively. So it's very effective for simplification. In fact, there are some expressions which are extremely difficult to simplify if you simply depend on the symbolic notation. But if you use the indicial notation, it becomes quite straightforward. And again, this is something we'll impress upon you through many examples today and later. Right, so now let's move on to the next topic, that is the scalar triple product. And I'll help you recall again that why are we doing this? Of course, one is to understand the various vector products, but that is not the main goal. The goal is to help us learn the use of indicial notation for applying these operations. So the scalar triple product between 3 vectors, as the name suggests, triple product, is defined as u dot v cross w. So u, v and w are 3 vectors. Now in this case, I have put brackets here, but you can choose not to have the brackets. Even then this would make sense, because if you do the dot first, then you are left with a scalar, and you cannot take a scalar crossed with a vector. So the only way possible is that first you have to evaluate v cross w to get the vector as a result, and then you take the dot between that vector and the vector u. But again, let's keep brackets for simplicity. So let's use the indicial notation. So that's how we'll typically solve or simplify expressions. We'll simply jump into the indicial notation. So u will be written as ui ei, and then v will be written as vj ej. Again, the choice of indices is yours. You just have to make sure that the indices for u, v and w are different. And the index for w we'll choose as wk ek. Now this is where I'll demonstrate to you the power of indicial notation. Now the first thing we'll do is we will evaluate this expression. So ui ei passes as it is. There's nothing we are doing to it. And then vj and wk are scalar components, so they are moved to the left. Now we have ej crossed with an ek. Now using the permutation symbol for defining the cross product between 2 unit vectors ej and ek, this is epsilon j k, let's define a new index q, eq. Okay, so the rule we have used is, I'll keep writing that so that it helps you. ej cross ek is written as epsilon jkq eq. This is what we had derived last time using the indicial notation definition of epsilon. So if you want, you can go back to last week's lecture notes and recall this. And as I said, we typically keep the epsilon on the left hand side. So let's do that in the next step. We move the epsilon to the extreme left, epsilon jkq, and then we have a vj and wk, but we also have an ui, and ui again is a scalar component, so all the scalars move to the left hand side. So we have ui, vj, wk, and what are we left with? Well, let's complete this. So we have used these, so we are left with is ei dotted with an eq. So the vector operation we have is ei dotted with an, right, well, I'm not putting an equal to, but equal to is implied, okay, just to save a step. So what next? Well, we can bring in a delta here, because we have ei dot eq, and that is equal to delta iq. And whenever you have a delta, you can apply the substitution property if one of the indices is repeated. In this case, the index I and the index Q both are repeated, so it's our choice. So we will use replace Q. So this becomes epsilon jki ui vj wk. All right, so this is the expression, and you already know that when you are working with epsilon, it's the order of the indices that matter. So as long as you maintain the same order, the epsilon value is the same. So epsilon, let's write it down. So epsilon jki is the same as epsilon kij is the same as epsilon ijk, because it's the same order of indices. So if that is the case, then we can write this as epsilon ijk ui vj wk. So let's box it, and this is nothing but the scalar triple product of the vectors u, v and w, which is actually defined as u dot v cross w. So I'll suggest you try it yourself to get a feel of the indicial notation. Now what we'll do is we can also write this expression. So let's do a bit more with it. I can write this as epsilon jki, because epsilon, well, we had started with epsilon jki, so I can write this as epsilon jki. So I'm going back to the same expression ui vj wk that I had at this step. So I am writing that again, but this time what I'll do is I will I'll represent this as vj wk ui, because see, u, v and w are all scalar components here, so the order does not matter. So I can write this as vj wk ui. Even then this whole expression expands to the same quantity. So why am I doing that? The reason I'm doing that is that, see, all three indices j, k and I are repeated. So I can write this j as something else. So I could replace the index j with something else. All I need to make sure is that the index that I have here is the same as the index I have here, because that's the index j in the above expression. Similarly, if I choose to replace the index k with something which is in the blue color, I just have to make sure that the index I have here in w is the same as the index I have here, which is the second index of epsilon. Similarly, if I choose to replace the index I with something else, I just have to make sure that they are the same as the third index of epsilon is the same as the index of u. because ultimately what matters is that they should expand to the same quantity. All these indices are dummy. So in this new expression, I use I here, I use j here, and I use k here. And that's completely allowed because both these expressions will expand to the same quantity ultimately. So now you can start to guess as to what I'm doing here. So this is epsilon ijk vi wj uk. Compare this with this. So if let's call it b, if b was the representation of a, so you can see that is epsilon ijk, the indices I, j and k in that order, and then you have ui vj wk. So that's equal to u dot v cross w. So with that pattern, this expression here is v dot w cross u. So what we have shown is that u dot v cross w is the same as v dot w cross u. So see the order: u, v and w. So here also you have the same order, u, v, w. So v, w, u, just like we had in the indices of epsilon. It's the same cyclic order. In fact, by that same logic, we can write this as w dot u cross v. So with the same cyclic order, all these quantities are equal, and that is the reason that the scalar triple product is sometimes written as with a box like this. It's also known as the box product u comma v comma w. It's your choice whether you want to write this as u dot v cross w, or v dot w cross u, or w dot u cross v. Again, this is the power of indicial notation, that we were able to show this very easily. With symbolic notation, this would have been slightly difficult. In fact, what we can also show, or in fact we've already seen that u dot v cross w is the same as u cross v dot w. So again, the order matters. So I can write the scalar dot product between the three vectors u, v and w as this, which is also the same as, I can do the cross between u and v first and then dot it with a w. Right, so let's now move on to the next product, that is the vector triple cross product. So the triple cross product between the vectors u, v and w is written like this. So you do a v cross w, and then you do a u cross that vector, that is v cross w. So let's jump into the indicial notation. So this I'll write as ui ei crossed with a vj ej cross wk ek. So first we will expand this. So we'll do it in one step. So ej cross ek will be written as epsilon jkq. We'll move the vj and wk because they are scalar components, and then we have an eq remaining. And now what we have is we have a cross of ei and eq. Everything else is a scalar component. So let's move the scalar component to the left with the e on the extreme left, which is a typical way to write things. So ui vj wk, and then we have an ei cross eq. And what is ei cross eq? That is again we write that as epsilon iqp ep. So what we'll do now is we'll move the epsilons on the left hand side then we have a ui vj wk, and then we have an ep. Now remember, this is a vector triple cross product, so the result is a vector. Now is that the end of it, or is there something else we can do? Well, we have two epsilons, so we are hoping that if one of the indices of the two epsilons is the same, then we can apply the epsilon delta identity. So here we have the indices j, k and q, and here we have I, q and p. So we can see that q is repeated. So what I need to first do is that I need to make sure that q appears on the extreme right, that is the third index for each epsilon. So I have to do a rearrangement on the second epsilon. So I'll do that first. So I'll write this as epsilon p I q, and this remains epsilon j k q. Now that we have the last index the same, we can apply the epsilon delta identity and simplify. So I'll write this as delta first, that is the first index of each epsilon, times delta second. So the second index of the first epsilon is k, and the second index of the second epsilon is I, minus delta first second times delta second first. Okay, then we'll open the brackets and create the two terms out of it. So we have delta jp delta ki ui vj wk times ep minus delta ji delta kp ui vj wk and the vector ep. All right, so now what we'll do is we'll apply the substitution property of delta, and we'll do it in one go because you have two deltas in each term. So let's deal with the first term first. So the two indices j and p of the delta. So let's see j and p. So we have a j and p here. So it's my choice. So I'll replace the index p with something else. So this becomes ej, and we have a vj here. Okay, so this delta is gone. Now let's go to the second delta. The second delta has the indices k and I, and we have an I here and a k here. So I'll replace the k with the I. So this becomes wi, and here we have a ui, and now both the deltas are gone. So we have successfully applied the substitution property in the first term. In the second one, I'll replace j with an I. So this becomes vi, and in the second delta, I'll replace the p with a k. So this becomes e k hat. Okay, again I request you to please pause this video and go slow so that you understand this or try it out yourself. So this let's write it simplified: ui vj wi ej minus ui vi wk ek. So what do we have here? Well, now what we'll do is we'll go back to symbolic notation. Okay, although this is the final expression, so I can box it. If I was to give the answer in the initial notation, this is it, but I'll go back to the symbolic notation, and this is where we'll see something interesting. So if I look at the first term, you have a ui wi, and that is nothing but the dot product between u and w. So we have to learn how to go back from the initial to the symbolic notation as well. That's also important. So it's u dot w, and then you have a vj times ej, and vj times ej is nothing but the vector v. because whenever we write a vector v in the initial notation, we write this as vj, right? So if you're going back, this is what it is. Let's go to the second term. So you have ui vi, that is the dot product between u and v, and then you have a wk ek, that is nothing but the vector w. So this will also box. So what have we shown here? We have shown the identity that the vector triple cross product, that is u cross v cross w, can be written as u dot w times v minus u dot v times w. Now this is actually a very interesting thing, that if I asked you to show this going from left to right, then it would have been a challenge if you wanted to stay with the symbolic notation. But with the use of indicial notation, it was very straightforward. In fact, I didn't even tell you what we are doing first, and this is what we got. And this is an important identity. People use this identity in different places in vector algebra. So this was very straightforward with the use of indicial notation. So time and again we have shown that indicial notation is powerful. So now what we'll do is we will do an example. So let's close this lecture with an example, and this example will again will show you the power of indicial notation with the use of vector operations. So the example is, well, the problem is that we have to simplify. So how do we proceed? Well, we jump into the indicial notation. ai ei, that's dotted with a unit vector n, so which is written as nj ej. So that's a dot of a and n, and then you have a vector n here, so which will be written as nk ek. The vector n appears twice in the mathematical term, but since we are basically writing that in the initial notation, so we have to use different indices, because there's no way we can use the same indices, because this nk ek is this n and this nj ej is this n. So let's write the second term. Now that we are writing the second term, I can start with the indices again. I don't need to invent new indices, because the rule that an index should not appear more than twice is for one mathematical term. So this is one mathematical term and this is another mathematical term. So when I'm writing the second mathematical term, I can start repeating the indices. Okay, sorry, this is an error in the problem, so this should be a n cross a cross n. We'll write a as aj ej cross nk ek. So we have to be very patient here, because the chances of us making an error are quite high, so we have to go slow. So first we will apply the dot between ei and ej. So we'll move the scalar components to the left. So I'll move all the scalar components to the left. So what that means is I have three scalar components here. So I'll write ai, nj, nk, and then we have a dot between ei and ej, so that becomes a delta ij, and we still have an ek, so that remains as it is. I will call this 1 and I'll call this 2. It's much easier if I deal with them separately rather than repeating or mixing them. So let's simplify 1 to the final expression and 2 to the final expression, then we'll add them. Okay. So we just wrote 1 as ai nj Nk delta Ij times Ek. Can this be simplified? Well, yes, because you have a delta, so we can apply the substitution property. So we have indices I and j, so I'll replace j with an I in the remaining expression. So this becomes A I N I N K E K, and there's nothing more we can do to it, so we will keep it as it is. So let's move on to the second term now. The second term is NIEI AJEJ cross NK EK. So we'll go step by step. The NIEI we'll touch later. First, let's expand this. So this becomes epsilon. So EJ cross EK will become epsilon JKQ EQ, and AJ and NK are simply scalar components. All right, so now we will move the epsilon to the extreme left, as is the typical trend, and then we have the scalar components Ni, Aj, Nk, and then we have an Ei cross Eq. And Ei cross Eq is simply epsilon I Q P times EP. So then we copy the other terms. Now we have to check if we can apply the epsilon delta identity, because we have two epsilons multiplied to each other. So we can see that Q is repeated. So I have to do some rearrangement in the second epsilon. So this can be written as epsilon P I Q, and the other terms stay as it is. So this is delta first times delta second minus delta second times delta second first. Right, so let's apply the substitution property. So we can apply it twice in each term because we have two deltas. So in the first one, I'll replace the P, and in the second one, I'll replace the K. So this will become Ni, Aj, and Nk becomes Ni, and Ep becomes Ej. Minus, in the second, we have J and I, so I'll replace the J, and in the second delta, I'll replace the P here. So this becomes N I AI N K E K. So this is our second term. So let's give it a blue underline. I'll go back up and I'll give this a blue underline as well. We don't need this numbering. So now we'll go back to our original expression and replace the values 1 and 2. AI Ni Nk Ek plus Ni Aj Ni Ej minus NiAi Nk Ek. So we can see that these two are the same. ai, ni. The order of ai and ni does not matter because they're scalar components, nk, ek. So this is basically a dot n times the vector n. You can see it here as well. It's n dot a times a vector n. They are the same, so they will cancel because it's the same quantity subtracted to itself, and we are left with this quantity. So the final is a j n i e j, right? And what is ni times ni? Well, n is a unit vector, so ni dot ni is basically n hat dot n hat, and a unit vector dotted with itself is a 1, right, by definition. So this is simply aj ej, and that is nothing but the vector a. Well, that's very interesting. Well, this actually is known as the projection theorem. We'll need to talk about it a bit because this is an interesting theorem. Although it was presented to you here as an exercise in indicial notation, but it is worth knowing about it because, as I said in this course, we learn a lot of expressions and theorems through problems in indicial notation. So it's worth keeping these things in mind. Although I won't ask these theorems in exam, but it's worth knowing them because you're learning the subject as a foundations in continuum mechanics. So if you have a vector A, let's say this, and you have a unit vector, which is, let's say, so unit vector is simply used for a direction. So if I take a component of A along n, because typically you do that, you do a component of A along a vector, and then you take a component of A perpendicular to that, so we call it A along n hat and A perpendicular to n hat. So these are just two components of A. Now what are these two components? If you look at this component, this is the vector A dot n, because A dot n is simply the projection of a vector along a given direction, and since we are talking of a vector component, so that's the direction is n hat. And the other one, which is A perpendicular n, is actually this n hat cross A cross n hat. Let's see. So what is A cross n? So if you look at the vectors here, so A crossed with an n, so if you do a right hand screw rule, that comes out to be inside the plane of paper. So that's A cross n. And if I do n cross this vector, so n is in the right hand side and this A cross n is inside the plane of paper. So if you do that again, the right hand screw rule, you get a vector in the direction upwards, which is what we have drawn here. Okay, so this is called the projection theorem, which helps us to write a vector as a sum of a vector along a given chosen direction n hat in this case, and in a direction perpendicular to n hat in the plane which is the plane formed by A and n hat. So this brings us to the end of this lecture. So let's summarize this lecture. So in this lecture, we gave you a lot of practice on initial notation through vector products, that is the vector cross product, the scalar triple product, and the vector triple cross product. In fact, we saw an interesting example of simplification where we used initial notation and also the epsilon delta identity to simplify to a very interesting expression. Again, doing that without the use of initial notation would have been quite challenging. So as a concept check, here's a problem for you. So you have to evaluate epsilon ijk aj ak. Again, this could be a tricky situation, so try to think, if you were using symbolic to indicial, what symbolic notation would give you this indicial notation. So we have to think in the reverse order as well sometimes. So in the next lecture, we will now talk about operations with higher order tensors and of course apply the indicial notation to make our lives easier. So thank you, and I'll see you in the next lecture.